Welcome everyone to another of the RSE seminars for this term. Today we've got Matt Graham from UCL ARC, who is a research software engineer or research data scientist. He's got a background initially in engineering and kind of information, more recently looking at sort of probabilistic computing. And today he's going to talk to us a little bit about automatic differentiation, an introduction to kind of what the technique is and some of the different ways it's done, but then also talking about kind of some of the software implementations and the pros and cons of that. And I guess particularly salient, given it underpins a lot of compute that's going on now. And this is sort of off the back of the machine learning coupling workshop we had in a couple of months ago here in Cambridge, where we touched on some of these subjects. So yeah, thank you, Matt.
Yeah, thank you very much, Jack, for the invitation today. So yeah, I'm Matt Graham, research data scientist at ARC. Although my job title is research data scientist, I still think of myself as more of a research software engineer. And yeah, I'll be talking about automatic differentiation today, as Jack said, beginning with kind of tutorial on what automatic differentiation is and how it compares to some other approaches for computing derivatives. But then going on to kind of discuss some of the software implementations and the issues that surround that, and some of my experiences using automatic differentiation in various research projects that I've been involved in. So just to kind of give a bit of a context of kind of my move into RSE, but also to kind of set the scene for why I'm interested in automatic differentiation. So I started my education as a kind of undergraduate in engineering, specializing in information and computer engineering. And that kind of was the start of my interest in sort of probabilistic machine learning, kind of Bayesian inference. So after finishing my undergraduate, I decided to go up to the School of Informatics in Edinburgh to do a PhD there, working on a kind of approximate Bayesian inference topic, specifically looking at this kind of class of algorithms called Markov chain Monte Carlo, for fitting models to data, but also kind of quantifying our uncertainties in those kind of estimates of the parameters of the models. And this is where I really started to use, but also get interested in automatic differentiation. After kind of completing my PhD finally in 2017, I did kind of standard saying of being like, okay, I'm not really sure what I want to do longer term, but I'll go and do a postdoc. I kind of stayed in the computational stats area, still using various autodiff tools at this point. So originally moved over to Singapore, spent a couple of years there before, at the time, what I thought would be a kind of interesting placement came up at joint between the Alan Turing Institute and Newcastle University, due to start in March 2020. So then I moved back to the UK right at the beginning of the pandemic, which wasn't fantastic timing. Spent a year at the Alan Turing Institute and Newcastle, but actually never went physically into the office during that time or met any of my colleagues. But what I did learn about while I was at the Alan Turing Institute was the kind of research engineering group there and this kind of role of research software engineering. So when I saw a position come up at UCL for research software developer, I applied for it and was kind of pleasantly surprised when I got the job offer. And that's when I first moved into this kind of RSE type role. So I've been at UCL since then. I had a slight change in job title from research software engineer to research data scientist a year after joining. But yeah, my day-to-day work is still more on the sort of software engineering side. It's just that I typically work, because of my kind of research background, on kind of computational statistics aspects of projects. So that's just to kind of give a little bit of an overview of kind of where I'm coming from for this problem. But why am I talking about automatic differentiation specifically? So I mentioned there that I first started using autodiff tools during my PhD, specifically in the sort of context of my research project, which was developing these gradient-based sort of derivative-informed methods for fitting probabilistic models to data and kind of getting distributional estimates of the parameters of those models. So I kind of racked my brains about this, but I think probably my first exposure to automatic differentiation, at least in terms of actually using tools, was via this probabilistic programming framework STAN that some of you may be aware of. So STAN provides a kind of domain-specific language for defining probabilistic models. But one of the kind of key sort of selling features of Stan over kind of computing probabilistic programming languages that existed before it came around was that it had an implementation of this kind of gradient-based Markov chain Monte Carlo method called Hamiltonian Monte Carlo. And so that required Stan to be able to differentiate through the probabilistic models that it defines. And Stan actually has quite a nice general purpose kind of templated C++ implementation of both reverse mode and forward mode, which are terms that I will define in a little bit, automatic differentiation in it. And it's actually an implementation that continues to remain quite kind of competitive in how efficient and kind of general purpose it is. But it is quite tightly coupled to the kind of Stan kind of framework. So yeah, I kind of played around a little bit with kind of Stan tooling in the course of kind of early parts of my PhD. When I went on to start kind of coding up kind of the research code for my own project, I was mainly working in Python, and I came across this project, Fiano, which actually has quite a long history. It was kind of brought around by the kind of the Montreal research labs in kind of machine learning. I think started back in 2007. And it was, I think, fair to say, the kind of precursor of a lot of the kind of big machine learning frameworks that people kind of think about today, things like TensorFlow, PyTorch. But it allowed you to kind of, using a little mini language built into Python to define computational graphs, again, another term I'll define later, but a representation of the computations that you want to perform, some sort of abstraction of the functions that you're working with, both compile those to kind of efficient C code that both could run on a CPU, but also on a GPU. So that was one of the big selling points about Fiano, but also importantly, that computational structure allowed them to be differentiated through. So it had an implementation of automatic differentiation in it. And actually, as is common when a lot of people use autodiff tools, one of the sort of blocking points I hit quite early was that some of the operations I was interested in using, specifically some sort of linear algebra operations, so particular matrix decompositions, and some kind of special functions weren't actually originally available in Fiano. So like this was kind of my first foray into the world of open source software development, and I kind of made a few small contributions to Fiano, adding some of the operations that I needed for my project. And actually, this was probably a major stepping stone on my route to becoming an RSE eventually, because I really enjoyed that kind of experience of kind of contributing to the project, first experience of opening pull requests, doing code review. And though Fiano itself is kind of no longer actively used, there's been a couple of forks of it, one of which still underlies the Python probabilistic programming framework PyMC. So there's a project now called PyTensor, which was forked off from Fiano, and it still is in use today. So while I used Fiano for a while, because of its kind of the way it's structured and that it is a little bit more oriented at these kind of machine learning use cases, I found it was a little bit difficult to build general purpose software on top of it. And towards the end of my PhD, when I was trying to wrap up a lot of the methods that I've been developing into a sort of more general purpose Python software package, I came across this project called AutoGrad from the Harvard Intelligent Probabilistic Systems, I think, HIPS group. So this had been released, I think, some point in 2015. I think I first started using it in 2016. But this was, like, for me, kind of a bit of a game changer in terms of it suddenly made auto differentiation from a sort of Python perspective, at least, a lot easier to use, to provide the NumPy-like interface. So if you're already familiar with kind of writing your code using kind of the NumPy paradigm, it was very easy to then get code that you could differentiate through. And it, yeah, it was, a really kind of nice readable implementation of the algorithms as well. And in fact, it's something that is still developed. It's not quite as active as it once was, but if you're wanting to learn more about autodiff, I'd really recommend just looking at source code of AutoGrad, or indeed they actually have a specifically kind of targeted for understanding autodiff sort of simplified version called autodidact, which is, yeah, really kind of a great way to kind of understand the nuts and bolts of how an autodiff engine is implemented. So after I kind of completed my PhD, during my postdocs in 2018 was when this framework JAX was first released, which is actually developed by several of the kind of core contributors to AutoGrad, along with kind of other people from Google. This is probably the AutoDiff framework that I am now most familiar with and still continue to use quite regularly. It has some kind of nice features, but we'll talk about kind of later. But it is compared to, I'd say, other Python kind of high performance kind of computing frameworks, things like TensorFlow and PyTorch. What I find nice about it is oriented at more general scientific computing tasks. So you can quite easily do numerical simulations using JAX as well as fitting neural network models. So since I've moved to being an RSE, one of the projects that I'm quite involved in is a JAX-based package for computing spherical harmonics transforms and being able to do this in a sort of differentiable and GPU accelerated way. So I've continued building tools on top of JAX. And more lately, I've been kind of looking at some of the tools available for AutoDiff in the Julia space, in particular this tool Enzyme, which we'll talk about a little bit later, for looking at how to propagate derivatives through some of the sort of Julia-based climate model components that are available. Okay, so that was all setting scene, but I haven't yet really explained what automatic differentiation is. So I'm just going to try to, starting from a high level and then drilling down, kind of define what I mean by automatic differentiation, both in terms of what it is, but also comparing it to some of the alternative approaches we have for computing derivatives. So at the kind of highest level, we can think of AutoDiff as a way of, given some function, which we consider as being composed of these, what we sometimes term primitive operations, so sort of the low level operations that we both know how to kind of, given their arguments, compute the output of, but importantly, we know the derivatives of. And so we can just get this from the kind of mathematical definitions that we know of how to derive derivatives. And we can think of any function as just being composed of some primitive set. And basically the chain rule, the kind of rules of differentiation, give us the recipe for, given a function which is composed of some basic set, how to take the derivatives of each of those kind of basic primitives, propagate derivatives through them through the whole function. And what AutoDiff is a way of doing this in a kind of algorithmic fashion so that we aren't having to do it by hand. So the sort of acronym AD sometimes also is expanded as algorithmic differentiation, which I think is actually probably a little bit more descriptive of what automatic differentiation is doing, because it's differentiating in this algorithmic fashion. I'm going to stick with automatic differentiation in this talk just because I think it is a slightly more well-recognized term, but just to kind of give that kind of handle if it is another term that you hear in some contexts. So automatic differentiation, as described here, is different from kind of finite difference-based numerical differentiation and symbolic differentiation, and I'll try to make that distinction a little bit clearer in some of these following slides. So AutoDiff has a really long history, dating back to kind of the earliest days of digital computers. And in fact, so Robert Bengert, who is, or at least I think his PhD thesis is claimed by some to be the first that was actually in then the new field of computer science, actually kind of wrote his thesis on effectively what we now know as forward mode automatic differentiation. And within this kind of conference paper published after he completed his PhD, he has this kind of nice summary of something that we kind of recognize even now as being automatic differentiation. So a procedure for automatic evaluation of the derivatives of arbitrary functions, with the key component being that we decompose the function by introducing the intermediate variables that we use when computing the different operations as part of that function, as a sort of series of elementary functional steps. So within machine learning specifically, we sometimes kind of hear references to reverse automatic differentiation as being called kind of backpropagation when kind of applied to neural network models. So there's a kind of independent or somewhat independent line of research that's gone on to kind of developing AutoDiff-like methods within that context. And there's also kind of strong parallels between specifically the reverse mode of automatic differentiation and kind of a joint sensitivity analysis. And in fact, you can kind of draw very close parallels between the two. Okay, so why should we be interested in automatic differentiation? So this first point, I think, is if you're going to take away just one thing from this this whole talk, I would say this is to me the kind of one of the most interesting things about autodiff, and something that wasn't at all, at least intuitive to me when I first learned it, that autodiff effectively allows us to compute gradients and other kind of derivatives very cheaply. So if we have a function from n inputs to m outputs, we know that we can always compute the full Jacobian of that function, so the matrix of partial derivatives, at a cost which is the smaller of the number of inputs and the smaller of outputs, times the operation cost of evaluating the function itself. And specifically, if we kind of think of this in the context of a scalar valued function of multiple inputs, so in that case, m is equal to 1, this is saying that we can compute the gradient of that scalar valued function at some constant factor overhead of evaluating the function itself. So this means basically that we can get gradients very cheaply, and because gradients in optimization and Bayesian inference and kind of other settings are very informative, allow us to get a lot better efficiency when they are available. This is basically saying that when we can use autodiff, we really should be using it to get gradients, because it's not really going to add anything to the overall complexity of our operations compared to just evaluating the function itself. And this is actually, I think this result, so this is a bit unclear who kind of first formulated it, but I think the kind of first somewhat formal proof of it was in this kind of technical report by Grivank on automatic differentiation, and it's actually quite a readable paper, so if you're interested, I kind of recommend looking through that. It kind of sets out in a fairly high level, but kind of instructive way, why we expect to get this kind of behavior in terms of complexity. So autodiff, compared to kind of manually differentiating for functions, one of the key advantages is that this is not kind of restricted to the things that we can mathematically write down on paper. It's any sort of function in the context of something that we can compute on a computer, and that can be expressed algorithmically, include use of kind of control for kind of writing to and from memory. We can differentiate through all of these operations, at least theoretically. So the other kind of part of this triplet I'd say about the advantages of automatic differentiation is that in as much as we can never have exact results when working with finite precision arithmetic on a computer, it provides exact derivatives. So we still suffer from the usual floating point arithmetic errors, but unlike numerical differentiation approaches, which have some sort of truncation error, we don't have that in autodiff. So we're getting things that are as close to exact as we could expect on a computer. So I'm just going to introduce a little bit of notation now. So when I'm kind of talking about the various different components of autodiff, hopefully it's a little bit more concrete. I'll try not to make this kind of too mathematically heavy, but I just wanted to be kind of outline the notation I'll be using, because it's not entirely standard, or at least not always the most standard notation. So if we're considering some differentiable function from n inputs to m outputs, I'm going to denote the component function, which gives you the value of that mth output as a function of all of the inputs, as just using this kind of subscript notation, so f subscript m. And the derivative of the whole function with respect to the nth argument is going to be this partial subscript f. And without subscript, partial operator applied to f is just going to represent the Jacobian matrix or a function that evaluates the Jacobian of that function f. So I've mentioned at various points numerical differentiation, but what do I mean by that? So this is effectively the kind of standard finite difference methods that a lot of us will kind of come across at various points, that are effectively based on limit definitions of partial derivatives, or alternatively on kind of Taylor expansions. So just kind of considering perhaps this sort of simplest case where we have some differentiable function, and we want to kind of get this kind of first order forward finite difference kind of expansion of the derivative. That just corresponds to saying that we'll perturb the input along one particular kind of axis of the input. So we'll add a small step size, we'll compute a difference between that and the valuation of the function at the original point, divide by that step size. And this, as mathematically at least, as h goes to 0, should converge to the derivative of interest. So I kind of made the statement about the efficiency of automatic differentiation previously, so that we can compute this Jacobian matrix at a cost which should scale with a minimum of m and n. But in contrast, when we're using numerical differentiation finite difference approaches to evaluate the full Jacobian matrix of a function with multiple inputs and outputs, we actually have to do a number of inputs times kind of scaling in of the function to get that full. So we can kind of compute this Jacobian matrix row by row or column by column. Can't quite work out in my head which way around this should be. But we do have to do at least n evaluations of f to get that full Jacobian matrix. So this is kind of most kind of burdensome or problematic is when we're working with the kind of common case of scalar functions, so where m is equal to 1 of a large number of variables. And so what this is saying that even though our function is kind of scalar valued and with autodiff, we know that we would be able to get the gradient at roughly the same kind of cost as evaluating the function itself. Here, the cost of evaluating the gradient is going to scale with the number of inputs, which for a large kind of high dimension input space is going to make this gradient a really expensive operation to use, and it kind of underlies why there is sometimes this intuition that gradients are fundamentally an expensive operation, while we know that they should actually be quite cheap to evaluate. There's also kind of some additional issues with finite difference approach that when we're using kind of small step sizes, just because we are working in floating point arithmetic, they can actually become numerically unstable. And so you often see these kind of classic plots showing how the overall error in that finite difference approximation to a derivative varies as a function of the step size. And there are kind of two competing effects here. There is a fact that we're kind of truncating a sort of Taylor expansion of the derivative. So we have this kind of truncation error, which gets larger as the step size gets bigger, because it's in the limit of that step size going to 0 that truncation error effectively disappears. But because we're in limited precision floating point arithmetic, and our finite difference approximations have this kind of difference term in them, we get this kind of catastrophic cancellation type effects, that as the step size gets smaller, we get a larger and larger kind of round off error. And this actually means that there is this kind of sweet spot or this kind of point of diminishing returns that, for example, for these kind of first order methods would typically be the square root of your kind of epsilon for the precision you're using. So here, 10 to the minus 8 roughly, where beyond which actually, if you push the step size smaller, you'll actually get a poorer approximation. So we're kind of like that both limits the approximation error that we can kind of push down to, but also that specific kind of step size you should be using is somewhat dependent on the function you're kind of working on. So it's something that you're going to have to kind of tweak carefully to make sure that you don't end up in that kind of catastrophic round-off error regime. So as a slight aside, but it's again something I was kind of interested to learn existed when I first heard about it, there is an alternative approach that's applicable to a subset of kind of specifically analytic functions for doing numerical differentiation that avoids this latter issue for numerical stability, called the complex depth method. So this is based on, again, kind of looking at this kind of Taylor series expansion of function, but here using a kind of imaginary perturbation from the original point. And if we just do a little bit of mathematics, so if we take the imaginary component of both sides of that truncated Taylor expansion, do a bit of rearranging, we can kind of show that the partial derivative of our function, if it's analytic, can be shown to be the imaginary component of the function evaluated at this imaginarily perturbed point divided by the step size. And the key thing to kind of note here is that there is no differencing operation going on. We're just evaluating f at this kind of complex point and dividing by a step size. And so this kind of avoids that catastrophic kind of round-off error that we get with finite difference approach. And actually, with a single kind of function evaluation here, the counterpart to that, it's a single function evaluation on a complex input. So it's really two function evaluations on the real and imaginary parts, but that we can get this kind of second order h squared accuracy. And we can push that h down right down to kind of floating point precision and still remain stable. So, if you happen to not be able to do automatic differentiation and you're working with an analytic function and want to get gradients, then this complex depth method can sometimes be a useful way to do that. So the other approach that we have available for computing derivatives on a computer is what's sometimes termed symbolic differentiation. So this is effectively the kind of derivative type implementations that we get in computer algebra systems. So things like SymPy, symbolic.jl and the Julia ecosystem. There's also a package in R called deriv, which effectively does symbolic differentiation. So the nice thing about symbolic differentiation is that kind of correlates a little bit more to when we're differentiating things by hand on pen and paper. So we get these human readable expressions as output. But the kind of flip side of this is because we're basically expanding the output of our function in terms of all of the input variables we're using as one kind of long, big, complicated expression, the derivatives are also then just all expressed as so the partial derivative of the output with respect to an input is entirely expressed in terms of the input variables itself, which leads to this really quick kind of exponential blow up when we have functions which are kind of composed of other functions, which is kind of commonly the case when we're working with models on a computer. And kind of beyond this fact that the expressions themselves just become unwieldy to work with, we're not really exploiting the fact that typically the different partial derivatives will have a lot of redundancy between them. Will be kind of common expressions there that we don't need to be evaluating separately. And we could apply some sort of common sub-expression elimination to the outputs of this, but that's kind of, it would turn out that autodiff kind of alleviates the need to do that. We kind of get this avoidance of this redundancy for free without having to do this kind of separate optimization step. And how it does this is basically just by kind of using what we kind of usually think of when we're kind of working with functions on a computer, that we want to modularize them, that we're not just expressing a function as one big long function where we do all of the operations in a single line. We're splitting it up into intermediate computations, possibly calling out to other functions. And we're computing the derivatives in terms of those intermediate values rather than just expressing everything as some big expression graph deriving from the inputs. So when talking about automatic differentiation, or at least within some frameworks, you'll quite commonly come across these terms of Jacobian vector products and vector Jacobian products. And I'm just going to define what they mean, and then also how we can kind of relate those to these ideas of the two modes of automatic differentiation that I've briefly mentioned but not explained yet: forward mode and reverse mode. So the Jacobian, so this kind of matrix or function which gives us a matrix of partial derivatives, we can think of it as a linear map from the input space to the output space of our function, and we can apply it to a vector within our input space. And this is just the operation we'll term a Jacobian vector product. So we apply this JVP operation to a function at a point with a vector, and that's just the product, the matrix vector product between the Jacobian and that vector. And the kind of error result that I presented around the efficiency of autodiff kind of boils down to this property that evaluating the Jacobian vector product of a function can always be done at a kind of order one overhead over the cost of evaluating f itself. There's a kind of dual or kind of transpose operation that we're also often interested in, which is what's sometimes called the vector Jacobian product. So here this is considering the transpose of the Jacobian as a linear map from the output space to the input space and applying that to a vector in our output space. So this kind of follows very closely with the definition of the Jacobian vector product. So we're just applying the transpose of the Jacobian directly to a vector, and we're using a particular notation here to represent that. And similar to the Jacobian vector product, it can be shown that evaluating the vector Jacobian product of any given differentiable function can be done at this kind of constant factor overhead of evaluating the function itself. So I said earlier that autodiff is basically an algorithmic implementation of the chain rule. So that's just kind of expanding what we mean by the chain rule in terms of the notation we're using. So if we have two functions, f and g, then the derivative of that composition of f and g can just be expressed in terms of the derivative of f composed with g in the product of that with the derivative of g. Or equivalently, if we define this intermediate variable y as the operation of applying g to x and z as f to y, in this kind of possibly more familiar Leibniz type notation, we have that dz dx equals dz dy multiplied by dy dx, which we can express as this product of these two Jacobians. So we now have the ingredients basically to define what forward mode automatic differentiation is doing under the hood. So the kind of key operation that we're doing in forward mode is or in any automatic differentiation, we're composing our the function of interest into these operations that we know the derivatives of. And so specifically when we're working with forward mode, when we say we know the derivative, we know how to evaluate the Jacobian vector product for those primitive operations. And then we're applying the chain rule to the composition of those primitive operations to express the Jacobian vector product of the composition in terms of the Jacobian vector product of the individual kind of constituents. And we can just kind of churn through the mathematics here, expand our definition of the Jacobian vector product. In terms of this composition, apply the chain rule to that. We're going to label, just for kind of convenience here, g of x as equal to y, and then just kind of simplify the notation that we have there, and we can kind of then relate that back to how we define the Jacobian vector product, that the Jacobian vector product of the composition is the Jacobian vector product of the outer function f at the point y, then applied to the output of the Jacobian vector product of the function g, evaluated at x at the vector v. So that's a lot of notation, but the kind of key thing to take from this slide in terms of when we talk about the properties of forward mode versus reverse mode automatic differentiation later, is that when evaluating this, we need the output of g of x, so that is y, at the same time as we are able to evaluate this Jacobian vector product of g. So here we need y only when we're evaluating the kind of outer Jacobian vector product here. So and by that point, we'll have already evaluated the Jacobian vector product of g, and so we can kind of evaluate both g and its propagate derivatives for it at the same time. And this is a kind of defining feature of the forward mode of automatic differentiation. So we can do the same sort of trick for the vector Jacobian product. Again, just expanding the definition, using here the sort of definition using the chain rule, then using that the transpose of a product is just the product terms transposed in the opposite order, so that we get that if we kind of continue with this, that again, labeling g of x as y, that the Jacobian vector product, the vector Jacobian product of this composition can be expressed as the vector Jacobian product of the inner function here, g, evaluated at the original point x, applied to the vector Jacobian product of f, evaluated at g of x, y, applied to the vector v. And so the key difference here compared to the Jacobian vector product is now we first evaluate inside the parentheses here the vector Jacobian product of f. And at that point, we need to already know y, and y is g of x. So we're kind of now out of sync. We're propagating derivatives through f, but we're needing to know the derivative of g. And this kind of underlies this property of reverse mode automatic differentiation, that we will need to record intermediate values that we use in computing what's often called the primal value, so the value of the function itself, in a forward pass before then doing a separate reverse pass using those intermediate values to compute the derivatives, to propagate the derivative from an output to the inputs. So just to kind of put that all together, so we consider a forward mode and reverse mode automatic differentiation is basically just defining a function as an arbitrary composition of primitives. And what we define as our primitives is one of the key ways in which we kind of structure our autodiff engine. So we can do that at a very low level. This can just be arithmetic operations and kind of think of everything as just being kind of boiling down to some very limited subset. But often in practice, we want to kind of use higher level operations. So if we've got linear algebra operations, we'll want to have those as primitives so that we can kind of define efficient derivatives of those operations in terms of other linear algebra kind of implementations, rather than just differentiating through the underlying sort of expanded definitions. And importantly, we need to be able to evaluate both the Jacobian vector products if we want to do forward mode, or the vector Jacobian products of all of those primitives. And so a lot of autodiff engines are effectively, one component of them will be a library of what the Jacobian vector product and vector Jacobian products are for a whole series of different operations. And we then just have some infrastructure for recursively applying the chain rule so that we can compute the Jacobian vector product and the vector Jacobian product for that whole function that is a composition of those primitives. But with the this kind of important caveat for the reverse mode accumulation autodiff, when using vector Jacobian products, we have to have this kind of two-pass type approach where we first compute and store all of the immediate variables in a forward pass, and then propagate derivatives from the outputs back to the inputs in a backwards pass. So just to kind of bring this to be a bit more concrete, if we're computing gradients of a scalar valued function, we can express this concretely in terms of a vector Jacobian product. Is just the vector Jacobian product where the vector, the seed thing that we're specifying at outputs, is just this scalar kind of 1. And this is what underlies that property then, that we can compute the gradient of a scalar valued function at a similar cost evaluating f of x. It's just a single vector Jacobian product operation. So let's just kind of look at what that looks like in practice for a particular very toy but hopefully instructive example of computing the negative log density of a univariate normal distribution where we have some mean and standard deviation parameters, m and s, and we're evaluating it at a point x. And we can just kind of mathematically expand this as kind of this function f of those three values, where we have this kind of simple here kind of form, and actually obviously the derivatives here are not difficult to work out by hand or to kind of express symbolically, but it at least fits on a single slide, and we can kind of see in practice how we use these various different differentiation approaches. So what would symbolic differentiation kind of correspond to? So in Python at least, we could use something like sympy. We could define symbolic variables for each of the different inputs to that function, build up an expression for that negative log density in terms of kind of sympy's kind of mathematical operations, and then apply the sympy diff function of that output with respect to each of the different input variables, and we'll get something that might render as shown here as these kind of symbolic expressions for each of those different derivatives. So here we're having to evaluate each derivative separately, and there's no kind of sharing of common sub-expressions. So we can see even in this really simple example, there's a lot of shared structure between those derivatives. So there's this kind of common x minus m difference term, there is this quadratic term in s. But if we were to kind of translate this kind of to kind of Python code, which sympy has support for, unless we were doing some sort of common sub-expression elimination here, we would basically for each derivative be separately computing that difference term and that quadratic term, which is partly what underlies the kind of inefficiency of using symbolic differentiation for these sort of tasks. So numerical differentiation, particularly a sort of first order finite difference, we could use something like NumPy to do that. Just define a point that we want to differentiate, define a step size here, because we're using a first order finite difference approach, and in single double precision floating point alpha arithmetic, we'd probably want to set that to roughly 10 to the minus 8, and we'd get some numerical expression out for the gradients. But here we need to evaluate the function with a number of times that kind of scales with the number of inputs, and the kind of, at least in this first order finite difference case, we're getting something that's approximate linear scales in the size of the step. We could use a complex step method here. It turns out this function is analytic, and we would get more accurate without kind of the same truncation error results here. And in some ways, we're kind of reducing the number of function evaluations, but again, that's kind of a little bit kind of hiding things away here because we're evaluating a function on a complex value, which is in itself more complex, more computationally costly than evaluating it on a just a real value. Okay, so that was the non-autodiff approaches. Now just look at 3 different instantiations of autodiff engines and what that looks like in terms of the APIs. So I mentioned this package earlier, Autograd. So Autograd provides this kind of drop-in replacement for NumPy. That you basically, the idea is you import autograd.numpy and then just define all of your functions in terms of that interface as opposed to the standard NumPy, and by and large it kind of follows kind of NumPy semantics, but it allows you to differentiate through. the functions that you define. And in particular, it provides these kind of functional derivative operators that you can apply that to a function and get another function out, which corresponds to the relevant derivative of that function. So here we apply the grad operator to our negative log density function. We specify we want to compute derivatives with respect to all three arguments. And importantly, this will give us kind of the numerically exact modulo floating point error derivatives out. And this will all be done in a kind of single forward and backward pass. So if we had more inputs here, this wouldn't kind of scale a computational cost. It would remain something that is just this constant factor overhead of evaluating the function itself. So JAX is a kind of another autodiff framework in Python that follows, and you kind of notice this here, the code hasn't changed much between these two slides because JAX was the API, it was entirely kind of meant to be very close to AutoGrad, and it kind of shares some of the same kind of contributors. But here, there are some kind of well, in this code example, it's not apparent, other than in the fact that the output here we can see, for example, is in 32-bit floating point precision. This is because JAX has made this kind of design decision to default to single precision because it's often used on accelerator devices where that is the sort of more useful to do, or you will get better throughput. You can choose to kind of explicitly flag to it to switch to kind of double precision, but this is one of these things, sharp edges that sometimes catches people out, that they would just assume that it's following this sort of NumPy-like type semantics, but actually you need to do a little bit of tweaking to get to that. But the kind of main advantages of JAX over AutoGrad are that it allows you to do not just autodiff, but these additional transformations like just-in-time compilation and dispatching to accelerator devices. But to me, at least, it still retains what was one of the really appealing features of AutoGrad, that has a very kind of intuitive, high-level interface that's easy to use and to build kind of packages and structure on top of. Just to give a non-Python example, looking here at Julia. So Enzyme is actually a non-Julia specific kind of project that looks at autodiff at quite a different level from these kind of Python-based tools, that it applies automatic differentiation on LLVM intermediate representation. And the Julia binders, I think, are the most kind of popular way that people use this tool, but it can also be used, for example, differentiate through C++, and any other language, technically at least, that can be compiled with the LLVM toolchain, although in practice, I don't think there's bindings for all of the language that would apply for. And yeah, at least in this specific example, it's fairly, I would say, easy to kind of use. There's a little bit more verbose than, say, AutoGrad and JAX, because of the greater generality that it tries to achieve. So in particular, JAX kind of assumes that the functions that it's kind of working with are pure, and in particular doesn't allow any kind of in-place mutation of the arguments of those functions. Well, if Enzyme is trying to work with a much broader range of functions, which include things like mutation of arguments. And so one of the repercussions of this is you need to be a little bit more careful about how you're specifying how derivatives are being propagated through this function. And in particular here, all of these active things that I'm passing to this autodiff method are basically labeling how I want these input arguments and return value to be kind of treated within the autodiff engine. Specifically here, we're considering them all as kind of not doing in-place updates, but there are variants here where we're going to kind of accumulate a gradient into a variable that's being kind of updated in place. So yeah, sorry, I'll just summarize as well as this thing. Okay, so I'm running a little bit close of time, so I think I'm going to skip over this section on computational graphs because I don't think it's going to kind of add too much to the discussion beyond what we've already had, and just go on to some sort of more general points around implementation details of forward mode and reverse mode. So because of the fact that we can kind of compute the forward and so the derivatives and the primal value of the function itself in this kind of single pass, generally forward mode automatic differentiation is a lot more kind of easy to implement than reverse mode. And typically implementations will therefore also be a lot more general purpose because there's kind of less infrastructure they're having to build to make this supported across a wide range of operations. And in particular, a kind of really common way of implementing forward mode autodiff is using a kind of dual number type, where instead of just propagating the kind of primal value, we associate another value with a kind of shadow of that type with it, and at the same time we compute the kind of primal. We also propagate the derivative alongside it by basically overloading all of the primitive operations we're kind of working with to work with these dual number types. So they compute both the kind of the forward primal evaluation and that kind of Jacobian vector product operation, which takes derivatives with respect to the inputs and propagates them with respect to the output. The kind of flip side, that while it's more implementationally simple, is that forward mode is in some ways the less useful of the two modes, because the really most common case by far is that we're kind of working with a scalar valued function of multiple inputs and want to compute a gradient of that. While forward mode is most efficient in the case where we have a multi-valued function with only a few inputs, because we're kind of scaling in the number of outputs in its terms of computational cost. So reverse mode has this kind of additional complexity that we need to do an initial forward pass before propagating the derivatives in a reverse pass. This means that we have to have a structure for recording the computation that's done in that forward pass. And this is where a lot of the complexity and implementation detail in autodiff actually comes down to. So they're kind of theoretical kind of constructs around this, things sometimes called like Venn lists for recording or tapes the operations that we're applying in a kind of graph-like structure to then allow us to, when we come to do the reverse pass, we both need to have the data associated with that forward pass intermediate variables, but also we need to do this kind of transposition reversing operation where we traverse that graph in the opposite direction from outputs to inputs. And being able to do this in a general fashion and kind of working with the full kind of complexity of all operations we want to do with a computer is where basically the difficulty in doing autodiff often lies. The other kind of sort of negative point around this is that as that computational graph gets larger and then the number of intermediate variables in it grows, so do the memory requirements. And that means that autodiff can be sometimes memory limited. So that, this is what underlies the increasing demand on kind of GPU memory for kind of training a lot of kind of modern machine learning AI models. It's effectively that we need to store this kind of full set of intermediate variables, at least with this kind of basic naive implementation of reverse mode. There are trade-offs you can make. So you can trade off doing more recomputation of intermediate variables without storing them in memory, and that will allow you to somewhat overcome this issue that memory requirements will still grow. But despite all of this extra implementation complexity, in some ways, reverse mode is actually the more widely applicable approach, because what it allows you to do is cheaply evaluate gradients. So there are many different frameworks for doing autodiff. We've come across some of these already, things like Autograd, JAX. There's also a preponderance of those in the Julia space as well. And kind of important question is how we choose which framework to use. And there are various axes on which we can do this. These are just kind of some of the ones that I think are important. So one of the kind of key ones that maybe sometimes filter out things at a high level at least are some of these frameworks are kind of quite clearly aimed more specifically at machine learning use cases. So things like TinyGrad, TensorFlow, to a lesser extent PyTorch. The way that they're structured makes them very easy to use in machine learning oriented workflows, but if you want to do kind of general purpose scientific computing, you're having to do quite a lot of extra work. One of the kind of the biggest differentiators is how kind of flexible the frameworks are, and whether we're kind of forced to work this kind of walled garden of kind of primitive operations. So things like JAX fall into this kind of setting where we have to define everything in terms of the JAX NumPy interface or the JAX SciPy interface. JAX also doesn't allow you to do mutation. As I said, it kind of works as pure functions, and at least within certain kind of restrictions, it's difficult to do dynamic control flow versus things like Enzyme, which aim to be kind of very general purpose. They're just differentiating through the LLVM intermediate representation. The kind of flip side of this, at least I find that these are somewhat anti-correlated, is kind of user-friendliness of these things. And that's probably because if you're kind of working in this more restricted setting, it's easier to have this nice, well-defined API and informative error messages. But yeah, I would find, say, tools like JAX, PyTorch, they're quite easy to use as a user. They have really good documentation. It's possibly also partly a reflection of the fact that, specifically in the case of JAX and PyTorch, that they have the weight of Google and or Meta behind them, and all of that kind of developer time. But actually, as a user, this is quite a key thing. Like, if you do get some problem with them, you're probably going to have a message that hopefully tells you what you need to do, or you're going to be able to find someone else who's had that same problem online. Versus Enzyme, where you can do a lot of tracking through kind of obscure Julia stack traces to try and figure out the origins of an issue. There's also a kind of related point around the sort of longer term stability, maintainability, maintenance of these packages. So a lot of autodiff engines or kind of research software, they're developed by, say, grad students, postdocs, and some of them kind of wax and wane in terms of popularity over time. So like Fiano fell out of kind of fashion. It has been resurrected in these kind of forks, but it's something to kind of consider specifically in the research software context of what you're building on top of. The least important factor, I would say, but it's often the one that people consider first, is performance. So these frameworks do have different performance trade-offs, but you're probably going to spend more time like writing and reading your code than you are running it. So I would say, while it's an important factor, you should make sure that these other factors are also kind of considered as well. But things like, whether or not the framework supports dispatching to accelerator devices, if there's ways, at least in the Python side, of avoiding the kind of interpreter overhead, can be important. Okay, so I think I'm pretty much at time, or already over time, so I'm just going to conclude with some final thoughts. So the kind of key message I would say here is, when you can use autodiff, and there's a big caveat of that, where you can, you always should, if it's available over kind of finite differences, for example, because you get gradients both more cheaply and more accurately. But there's, in practice, very rarely the case that you will just be able to take some existing code base, particularly if it's a kind of a legacy code base, and throw it to an autodiff tool and get gradients out of it. You're going to have to do a little, at some level of re-implementation, and there's a sort of sliding scale of what that means there. But the payoff is that you will maybe be able to get derivatives out of it, and that's a very powerful thing for optimization, for calibration of models. All of these different frameworks have very different trade-offs along these different axes. And yeah, as I said, I would kind of not just think about on the performance axis, but things about the kind of flexibility and their ease of use as well as performance. And actually also a kind of really key point is, trying to, both use tools that are going to have long-term maintenance, but also the kind of flip side of that, if you're using tools, thinking about contributing back to them so that they do remain stable in the longer term. Okay, so that's me at time. Thank you for listening, and apologies for running a bit slow there. And if you are interested, I'll post the slides. There are some interesting resources you can look at on automatic differentiation.
Super. Thank you very much, Matt. And I was going to say, if we could get the slides, that'd be super useful. I think we have time for maybe one very quick question, and Sherman has got in there first, who said, do you use the second derivative in your work, for example, Hessians, and is it a good idea to use AD tools for this as well?
Yes. So actually, that was one of the things that I first found quite difficult about a lot of machine learning oriented autodiff packages, is that like getting second order derivative information is not really a priority for them. Typically they're just using sort of first order stochastic gradient descent methods. Things like JAX do allow you to get out second order derivatives. And there are various ways you can do that. And I'm rarely computing the full Hessian matrix, but computing kind of the action of that matrix on vectors or kind of variants of that can be really useful, and it underlies some of the sort of Markov chain multicolor methods that I was working on. So yeah, you need to be specific with the framework to use, because not all offer support for kind of higher order differentiation, but where you can, it kind of multiplies the kind of benefits you're getting.
Super. So yeah, I would say Matt's around sort of for a bit longer this afternoon, and we'll be hanging around here. We're heading over to the Ocean building. So if anyone does have questions or wants to chat, please do. Other than that, if we can finish just by thanking Matt once again